Hello everyone, welcome to the fourth lecture, and in this lecture we are going to see about three body problem. Hope you have clear understanding about the two body problem, in which we have seen like how two bodies in the universe interact with each other under the influence of gravitational force alone, and also we have derived by considering one object as a very small object compared to the other, so one being primary, other being the secondary. Under that condition, we have derived the equation of motion for that secondary object, and we also have derived the equation that governs the energy, or that explains the total energy at any point for that secondary body. Okay, that is what we have done in the two body problem. Now we are going into the three body problem. So here it is called as restricted three body problem because of the considerations or assumptions whatever we have taken. So this deals with motion of small mass in a gravitational field of two larger masses. So here we have considered in the restricted three body problem, we don't have to care about the n body problem or the generalized form. So here with this assumptions we are going to derive. So this problem, the three body problem with this assumption, is also called as restricted three body problem. It deals with the motion of small mass in a gravitational field of two larger masses, where the smaller mass is assumed to be negligible compared to the larger mass. Let us consider there is a sun and moon. Let us consider there is an earth and the moon, and you are launching a satellite under the influence of both sun and moon. Then you are launching a satellite. The size of the satellite is very small compared to the size of earth and moon. Also, if we are launching a satellite, if you are launching a satellite for between interplanetary launch, like we are trying to launch a satellite for other planets apart from the own planet where we are living, then under that case a three body problem comes into picture. Okay, so this problem arises in various astrophysical scenarios such as motion of satellite around the planet and moon and a moon around its planet, or motion of planet around its parent star, and in the context of binary star system. Okay, in the restricted three body problem we have considered a three body system where two primary masses, large bodies, are in circular orbit around their center of mass. They are in the circular orbits around their center of mass, and the third mass is much smaller than the primary mass and moves in their gravitational field. So m1 m2 together create a gravitational field in which the m3 is moving, and the m3 is of very negligible size, so we can ignore how the mass of the impact of mass of the smaller object m3. Okay, here the inertial system is shown in the figure 1. Okay, the inertial system is shown on this figure 1. Okay, here you can see the axis capital X, Y and Z, and this forms capital X, Y, Z, Z. This forms the inertial frame, and the small x, y and z form the rotational frame. Again, we'll come to this when we are going into the concepts. Okay. In this case of three body problem, understand the essence of it, because the derivations of the equation trace back to a lot of concepts which is not in our scope in this subject. Okay, it is not the scope of this subject as of now. For the syllabus point of view, it is not in the scope. Okay, so first let us consider an inertial frame X, Y, Z, capital X, Y, Z, with its origin at the center of mass of the system. So the origin is at center of mass of the system. We have system where P1 and P2 are the larger masses, P is the point of the small mass. Okay, the center of mass will, as a consequence of our assumption, lie in the point connecting P1 and P2. This is the center of mass which is at the origin, and it lies in the line connecting P1 and P2, obviously. Okay, because of our assumption, because we have said origin is at the center of mass, which means that P1 P2, line connecting P1 P2, should pass through the center of mass, right? Okay, the position vectors of R1 and R2 we can write as, because the position vectors m r1, position vector of the center of mass with respect to that point is 0. So because of which m1 r1 plus m2 r2 is equal to 0. From that r1, this is the derivation which we have already seen in the two body problem. So r1 is equal to minus m2 by m1 into r2. So the angular momentum of the system is constant. We know that by the law of conservation of momentum, the angular momentum of the system is constant. So which is h is equal to m1 r1 cross, this is nothing but the linear momentum into, this and this forms a linear momentum, mass into velocity with the position vector. The product of linear momentum and the position vector is nothing but the angular momentum. The same thing has been done and it is a constant. Okay, so the angular momentum of the system is constant, not an individual body. The system is constant. Now I am trying to substitute the expression 1 in this, in equation 2. Okay, so I can have two things, one equation, like I can represent the equation in terms of R1 or in R2 alone. I can represent it in terms of R1 or R2 alone, because R1 can be represented in terms of R2 and R2 can be represented in terms of R1. So because of which I am getting two expressions where H is equal to M1. Here this R2 is replaced by R1. Okay, so when I am replacing R2 by R1, R2 is nothing but minus M1 by M2 into R1. So it is minus M1 by M2 into R1, right? So that is what we are doing. So here I have taken this as my R. So I am substituting it here. So when I substitute it here, I get M1 into 1 plus M1 R1 into R1 cross dR1 by dt. Okay, so when I substitute it here and when I rearrange this expression, I will have 1 plus M1 here. This H1 is nothing but angular momentum, which means this M1 into dR1 by dt is the linear momentum of mass M1, right, into this R1 position vector gives rise to the parameter H1. H1 is nothing but the angular momentum of the object, or the angular momentum with respect to the body P1. Okay, angular momentum of body P1. Similarly, H2 is nothing but angular momentum. H2 is nothing but angular momentum of body. So that is nothing but M2 into dR2 by dt, which is nothing but a linear momentum, into the position vector R2. This will lead to the next thing. This is nothing but this will lead to H2, which is nothing but the position or the angular momentum of body P2 respectively. So where H1 and H2 stands for the angular momentum of bodies P1 and P2 respectively. By inspection of equations 1 and 3, by inspection of equation 1 and 3, we conclude that two massive bodies move in one plane. So the massive bodies P1 and P2 are moving in the same plane, one plane. They are always in a plane. So the XY plane, it is in the plane, it is in XY plane. Okay, it is XY plane. The XY plane in the figure has been chosen in such way that it coincides with the plane of motion. It coincides with the plane of motion. That is how we have taken this reference frames. Okay, we now introduce another reference frame X, Y, Z at the origin. So where its origin is at the center of mass of the system. The same system, we have the system X, Y, Z, which is an inertial frame system. In the system, we are introducing another coordinate X, Y, Z. So this is the another coordinate which we have introduced. Okay, this is introduced in the same system. Here, when we see this system like X, Y, Z is introduced, and with X axis coinciding with the line P1. See, the X axis is coinciding with the line joining P1 and P2. X axis is coinciding with the line joining P1 and P2. And it is making some angle with Z axis. Okay. So now the positive Z axis is directed along positive Z axis. Okay. Now the XYZ frame thus rotates relative to XYZ frame. This XYZ, the small XYZ frame rotates relative to. So the Z and the capital, the smaller Z and the capital Z coincides. In the positive coincides with the positive. And other thing, this XY frame is chosen in such a way. The small XYZ frame is chosen in such a way. The X-axis, the smaller X-axis coincides with the point, the line connecting P1 and P2. It is coinciding with the line connecting P1 and P2. The bodies P1 and P2 are fixed. Let me finish the first point. The X, Y and Z frame thus rotates relative to X, Y and Z frame with a constant angular velocity ohms, that is omega, with a constant angular velocity omega, about the z axis. It is making an angle omega with respect to the z axis. If this is the z axis and this is the x and y, x and y, this x and y is creating a rotation movement with respect to the z axis, like with respect to the z axis, and that angular velocity is nothing but your ohms. Okay, you consider there is a line, you have a thin wire in which you have a paper. You are rotating the paper around the when you are inserting a thin wire into a paper and you are rotating the paper. So you can consider the paper as a plane xy and the line is nothing but the z axis. So this is how your small xyz frame is rotating related to the capital xyz frame, and with an angular velocity omega about the axis. With an angular velocity omega with about an axis z. Okay, about an axis z. Then the bodies P1 and P2 are fixed related to the frame xyz. They are fixed related to the frame x, because you can see now what we are trying to do, the small xyz is the frame in which we have already aligned the x-axis in P1 and P2. The rotational motion of P1 and P2 is almost captured by the small xyz frame. If r is the position vector of the third body P in the rotating frame, the radius of the vector r1 and r2 to P is denoted by the radius of P1 and P2 to the point P is denoted by R1 and R2 respectively. The equation of motion of P, the equation of motion of P. Now we know this is rotating along with XYZ frame because its position is fixed related to XYZ frame. The P1, P2's position is fixed related to XYZ frame. Now we want to find the equation of motion of the point P relative to the rotating frame, according to the equation of absolute acceleration, which was there. You don't have to think too much. This is an equation of absolute acceleration from which they have finally written this. So what we have got is this is the part, like this is the, we know this is the force equivalent. From that, like we have finally got G. This is nothing but acceleration equivalent. When I take r common, this is subtraction of r equivalent, right? So this is, we have seen in the two body problem, G m1 by r cube into r1 is from the object r1, this is from the object r2. So when I subtract these two, I have got this, and this is equal to the rotation motion, how it is rotating, the angle. So rate of change of this angle, phase angle, angular velocity cross r plus omega into omega cross r plus 2 omega cross del r by del t plus del square r by del t. So this is the this is taken from the absolute equation of absolute acceleration, from the equation of absolute acceleration. So then now, where in this del by del t indicates time derivative of the rotating frame. So it is rotating with respect to time. So it is a time derivative of the rotating frame, because omega is a constant vector. It is a constant vector. Now, when we are simplifying this expression by keeping this here, okay, by bringing this to the another side, this is the final expression what we have got. We have got the terms, term 1, term 2 and term 3. In this the second and third term on the right hand side of this equation represents this represents the centripetal acceleration, and this represents Coriolis acceleration. Okay, so this represents acceleration due to the rotation of the frame xyz. So this is the final expression, and this term represents the centripetal acceleration. This term represents the acceleration due to this the Coriolis acceleration. These are the two accelerations represented by this equation. Okay, so because it is enough if we remember what are the parts of this equation from which we will derive the Jacobi integral. The Jacobi integral is actually says the total energy in total mechanical energy available. So we will see it in the later part. So now, as of now, this is the equations that is handling the rotating frame. So this the third term is nothing but centripetal acceleration. So we know what is centripetal acceleration. Centripetal force is a force that is acting perpendicular to the linear force. Okay, like for example, if there is an object, central object here, and you have a object which is moving this way, there is a force which is pulling it towards the central primary object. That is something but your centripetal force, which is pulling inward. We know centrifugal force is something which is pulling outward. Okay, so the centripetal force acceleration. Okay, this acceleration actually holds the object together with the primary object. Now, in this we can prove that the potential energy. So here you can see here this one is the centripetal force. This first one is this is due to the centripetal. The second term represents the centripetal acceleration, and the first term represents the energy, potential energy, normal energy. So now we can say that in the right hand side, the first two term forms a potential function. I have written the first two terms in terms of like expanding in the terms of this is in the vector r, so I am replacing it by x, y and z coordinates, because the r can be resolved into x and y coordinate and angle is in the z direction. So omega z the whole square into x square plus y square. Okay, that is how this part become. It is resolved into x and y component. So this is the potential function. Obviously the potential function is not only potential function obviously is accounted by the gravitational force but also by the centrifugal force. So accounts not only for the gravitational force but because of the centripetal force also there will be a potential energy. But we can for sure cannot introduce add the third term into the third term can never be added to the potential energy, because here you have dou r by dou t, which is nothing but the velocity term, which means there is an acceleration present. This represents a kinetic energy and not the potential energy. So we have the potential energy equation here. The potential function is not only accounts for the gravitational force but also for the centripetal force. The introduction of this potential function is possible because r1, r2 and omega are constant vectors in the xyz frame. In the xyz frame, the r1, r2 and omega are the constant vectors. Okay, now I can write z in the form of this is with respect to the angle. The omega is only with the angle is with respect to z line, and this is nothing but the unit vector. Ez is nothing but the unit vector along the z. It is evident that the Coriolis equation cannot be incorporated in the potential function because it contains the velocity of the third body. Okay, and the potential function equation can be written in the form. This can be written in the form like now equation 5. This equation can be written in the form by incorporating the potentials. By incorporating the potentials inside. By incorporating the potentials inside, the same expression can be represented by, see here this is there now, so this is nothing but this can be represented by, so this is the potential. If this is the potential, you can see this is nothing but the differentiation of this. This is nothing but the differentiation of this. So I am writing this as difference del u minus 2 omega in cross del r by del t. So this is the expression. So the first two terms are represented by the potential function. So next we are going for the Jacobi's integral. When we come to the case of Jacobi's integral, Jacobi integral is the fundamental concept in the celestial mechanics. So finally, sorry, I have not concluded it. So this is the potential function. Using the potential function, the final equation of rotation or the rotation of the vector. See this r vector, which is nothing but the rotation of the point P. The rotation of the point B with respect to the frame x, y, z. With the rotation of the point P with respect to the x, y, z. The rotation of the point B with respect to x, y, z is the acceleration of that point is given by this expression, where this is nothing but the potential energy and this is nothing but the kinetic energy. Okay, it is given by these two. Okay. So this is how the three-body problem is explained. So the solution to the three-body problem is not available, but the approximate solutions are available, with which only till now we are launching so many satellites, but the exact solution is not found yet for the three-body problem. So don't confuse too much into the three-body problem. So I want to give a overview once again. In the three-body problem, again we have taken into account that there are two frames. One is the frame which is a fixed inertial frame. Other one is a rotating frame, in which the objects P1 and P2 are present coinciding along the x-axis, and it is rotating. It is rotating with reference to the inertial frame, and it is forming an angle of omega with respect to the inertial frame, and that is constant. And now we are finding the momentum for the object P1 and P2, and finally we are trying to P1 and P2, and we found that also using the equation of absolute acceleration, we have also written the expression of the position vector P rotating, the position vector of the point P R, the rotation of the position vector or acceleration of the position vector is written from the absolute acceleration equation. When the equation is simplified, we found that there is a potential function and the centripetal force is included in the equation, and the last term of the equation is actually from the Coriolis acceleration. So that is actually contributed by the kinetic energy of the body. So finally the acceleration consists of two terms. One is the potential energy of the body, that is mass, and then another, it is an addition of total energy in the system. The acceleration, the total energy of the system, is represented by the potential energy, sum of potential energy and the kinetic energy in the system. So that is how the potential function is finally written. This is a final form of potential function. The next thing what we are going to see is the Jacobi's integral. So Jacobi's integral is a fundamental concept in the celestial mechanics and the study of conservative dynamical system. So the conservative dynamical system is nothing but the system which follows the law of conservation of energy. Okay, it arises in the context of the motion of a particle under the influence of conservative force, where the total energy of the particle is conserved. The Jacobian integral is particularly relevant to the study of restricted three-body problem and other central force problems. In the context of the restricted three-body problem, the Jacobian integral is defined as, for a particle moving in a gravitational field of two primary masses m1 and m2, Jacobian integral J is given as 2t minus u, where t is nothing but the kinetic energy of the test mass, which is 0.5 into we know half mv square is nothing but the kinetic energy of that mass or test particle, where in which in the half mv square, m is the mass and v is the velocity, and u is nothing but the effective potential energy of the test mass in the rotating frame. Okay, it is the effective potential energy of the rotating frame. Similarly, now what we are going to do, we have derived the final expression like equation 8 in the three-body problem. In that, we are going to multiply a scalar dou r by dou t to that. So when we multiply it and rearrange these expressions, when I multiply it and I make some little arrangement in this rearrangements here, then I'm getting the final expression. Then when I make the rearrangements, we'll get the expression in such a way like v square plus 2u is equal to minus c. We are getting that after so equation 9, after integration, it will lead to v square plus 2u minus 2u is equal to minus c, where p is the velocity of the point P relative to the rotating frame xyz, and c is the constant of integration. So the equation 10 is nothing but the Jacobi's integral. This is the Jacobi's integral. Okay, this is nothing but the Jacobi's integral. So we have just what we have done is rearranging the things. And finally, so we know this is, see, you can see here, this is nothing but du by dt. So from the expression, like from this expression, we are actually simplifying and integrating to get this expression v square plus 2u is equal to minus c, where v is the velocity and p is of a particle p relative to the rotating frame xyz, and c is the constant of integration. The equation 10 is known as the Jacobi's integral. So let us see why the Jacobian integral is very important. The first one is conservation of energy. The Jacobian integral remains constant throughout the motion of the test mass. It's going to be constant because the c is constant here, and as we see, v is nothing but the kinetic energy and 2u is nothing but the potential energy. So whatever the general form of the expression we have seen, so this is the general expression of the Jacobi integral. The same thing has been derived, can be derived from the same thing can be derived from the three body problem. Okay, so don't go too much into it. So when we take this expression and multiply, we can derive it, we can finally arrive at the expression v square plus 2 u is equal to minus c. So where this expression is nothing but the Jacobi integral. V square stands for the kinetic energy, whereas 2u stands for the potential energy. So this together is going to be constant. Okay, one and this together is going to be constant, which means law of conservation of energy is maintained. Okay, Jacobian integral remains constant throughout the motion of the test mass, because either if the speed of the kinetic energy is increased, your potential energy will go down. If your potential energy is increased, then the kinetic energy will go down. The energy is going to be constant. It is not going to change. So the Jacobian integral remains constant throughout the motion of the test mass. This is because the system is conservative and the total energy of the particle is conserved. The total energy of the particle is conserved. The effective potential, so that is about the conservation of energy. Effective potential energy. The concept of effective potential energy accounts for the centrifugal force. So it is not just a potential energy, it is called as effective potential energy, where we have incorporated the centrifugal force experienced by the test mass in the rotating frame of the reference. So it is derived from the classical gravitational potential energy, includes the effect of rotation of two primary masses around the center of mass. It is just derived from the classical gravitational potential energy, but it includes the rotation, okay, effects of rotation. So that is nothing but the centrifugal forces are taken into account. Okay. The next one is the Lagrange points. We will see what are the Lagrange points available. So in the restricted three body problem, Jacobi integral is especially important in the analysis of the Lagrange points. So these are the points in the space where the gravitational forces from the two primary masses and the effective centrifugal force on the test mass balances. So we can see here, this is the points on the space where the gravitational force from the two primary masses and the effective centrifugal force. So gravitational force is something which is pulling inside, and the centrifugal force is something which is pulling the object outside, and they are in balance, which means it maintains in the orbit. It is stable in the orbit. Okay, it is neither pulling inward, it is neither pulling outward. The object which is under rotation can remain stable in the orbit at this Lagrange points. It is also called as liberation points. So allowing the test mass to maintain a stable position relative to the two primary masses. Okay. The final thing is stability. The stability of the Lagrange point depends on the value of the Jacobi integral. The value of J is positive, then the Lagrange point is stable. Example L4 and L5. If the value of Lagrange point is negative, then it is not stable. So we have seen we will see the points. Now let us see the Lagrange points, which is also called as the liberation points. So with that we will understand which points are stable, which is not. Okay. The next topic we are going to see is about the liberation points. So liberation point is also known as Lagrange points. Okay, the specific point in the three body system where the gravitational forces of two larger masses and the smaller mass. So the gravitational forces of the two larger mass and the smaller mass balance in such a way that the test mass remain in a stable relative position with respect to the two larger masses. These points were first discovered by the French mathematician Joseph Louis Lagrange in the year of 1772. So in this context, we will see about Lagrange points. Why Lagrange points denoted with respect to in the context of three body problem, we will see like 5 Lagrange points denoted by L1, L2, L3, L4 and L5. Now each Lagrange point has its unit property and stability characteristics. We will see how it is working. Okay, the first is Lagrange point 1. The L1 Lagrange point lies in the line connecting two large masses M1 and M2. So this is lie in the point here. It is shown for the Earth, and when we consider the system Earth and Moon, they have mentioned these Lagrange points. So L1 is the Lagrange point which lies in the line connecting, okay, it lies in the line connecting line connecting the masses M1 and M2. It is usually located closer to the more massive body M1. It is located to the more it is located to the massive body M1. So usually located in the more it usually located closer to the more massive body. At this point, the gravitational attraction of more massive body M1 and the centrifugal force due to the orbital motion of the test mass. So, gravitational at this point, the gravitational attraction of more massive body, okay, and the centrifugal force due to the orbital motion of the test mass balances out the gravitational attraction of less massive body M2. So if the rendu like these two, which one? The gravitational force of the M1 and the centrifugal force, these two balances out the gravitational attraction of less massive body M2. The L1 point is useful for certain space missions and satellites, since an object placed at this point will have same orbital period as the two larger masses and will maintain stable position with relative to them, and it will maintain the stable position relative to them. Okay, so you can see here when it is launched in this L1 point, then it has the same orbital period as the two object, and then it is also stated that the position of that satellite launched remains in the stable position relative to the two massive bodies. Okay, so however L1 point is unstable. The test mass drifts slightly away from L1 position. The gravitational force will dominate, causing the object to move away from the point. Of course, the both centrifugal and the gravitational force compensates the gravitational force of the mass M2. So even if it is drifting, so we know when we put the object in an orbit, it drifts because it has its own velocity. If it drifts even a little, or due to some weathers or some atmospheric drag, so whatsoever at rest, under any condition, if the satellite from in the point L1 drifts slightly away, it's not larger, slightly away from the position L1, the gravitational force will dominate and causing the object to move away from the point. Okay. Now, L2 Lagrange point. The L2 Lagrange point also lies in the line connecting the larger masses M1 and M2, but it is also located on the opposite side of more massive body M1 from the larger mass. It is also located on the it is located in the opposite side. So see, it is from, we have seen L1 here. So L2 is here. Okay, but it is located to the opposite side of the more massive body. Here is a more massive body. It is lying opposite to the more massive body. Again, it is it is still on the line connecting the two larger masses M1 and M2. So at this point, the gravitational attraction of more massive body M1 and the centrifugal force due to the orbital motion of test mass M balances out, and the gravitational attraction of the less massive body M2. Here at this point, the gravitational attraction of more massive body M1 and the centrifugal force due to the orbital motion of the test mass balances out the gravitational attraction of the less massive body M2. Similar to the L1, L2 is also useful for certain space missions and observations, since the object placed at this point will have same orbital period as two larger masses and will maintain a stable position relative to them. Like L1, L2 is also point is also unstable, and slight disturbance will cause the object to move away from this point. The third Lagrange point, L3, is the point that lies on the line connecting the two larger masses M1 and M2 in the direction opposite to the side of the less mass. So here is L3. Okay, at this point, the gravitational attraction of less massive body M2 and the centrifugal force due to the orbital motion of test mass M balances out the gravitational attraction of the massive body M1. Okay, unlike L1, L2, L3 is point is unstable in two body system, and it is not a stable location for a test mass. Okay, now The last two Lagrange points are L4 and L5. So the L4 and L5 are here. Okay. So L4 and L5 forms equilateral triangle with the two larger masses M1 and M2. So L4 is located ahead of mass M. It is located ahead. See, if there is a mass M, it is located ahead. If this is a mass M, it is located ahead of mass M. Okay, in the orbit of L, in its orbit, while L5 is located behind it. Okay, if this is the orbital direction, if here it is the M object rotating, so L4 will lie ahead of it, L5 will located behind it. Okay, at this point, the gravitational forces and centrifugal forces due to orbital motion of the test mass form a stable configurations, and L4 and L5 are the stable locations, and small deviations from this point will cause the test mass to oscillate around them. Okay, it will not go out of the path, it just oscillate around them. So nothing, it is a stable position. It's not like the previous thing. Okay. So L1, L2 and L3 in the Earth Sun system. So when that was the case, in the Earth's Sun system, L1, L2 points have particular interest for the space mission. The James Webb Space Telescope is an example of space observatory placed at L2 point, allowing it to maintain a stable position related to the Earth and the Sun. L3 is not a stable point in the Earth-Sun system, so no significant object has been placed in the location. So Lagrange points play a crucial role in the space exploration and satellite missions. They provide stable location for positioning of the spacecraft and observations related to multiple massive bodies. Understanding the dynamic of these points is essential for mission planning and designing a stable orbits for various applications. So we have seen a restricted three-body problem where the third mass is considered to be very small compared to the mass M1 and M2. So the gravitational the third object or the satellite, which is test object, which is under test mass will be under the influence of the gravitational field of M1 and M2 together, and that forms the inertial system. Here we place the mass M1 and M2, the larger masses, in the rotational frame, and we have found the rotation. We have found the position of rotation of P with respect to the rotational frame XYZ, and also finally we have derived the equation governing the energy of that third mass under the influence of the gravitational field of M1 and M2, and it is governed by the equation that is governing the energies, the total energy or total mechanical energy of the system is called as a Jacobi integral. So in that Jacobi integral we have the mass total Jacobi integral. The integral has both potential energy part and the kinetic energy part. The potential energy is called as the effective potential energy, which takes into account of the centrifugal forces, the centrifugal forces into picture. So that is why it is called as the effective potential energy. So the Jacobi integral mainly focus on the law of conservation of energies. It actually is applicable for all the system that operates on the conservative energies. Okay, here like Jacobi integral states that the energy of the system remains constant. Total energy, mechanical energy of the system remains constant. We eventually know if a body is in motion, if its kinetic energy increases, obviously its potential energy decreases, and vice versa. So that is what the importance of the Jacobi's integral. So from the Jacobi's integral, we are finding a few points. Those are the liberation points. So for our syllabus, it is not necessary how to go and identify. It is sufficient. We know what are the points. We have some liberation points. Under the context of three-body problem, we have 5 liberation points: L1, L2, L3, L4 and L5. And these 5 liberation points are the points where the force is gravitational and the centrifugal force balances out each other. So gravity pulls the object inward, centrifugal force push the object outward, and it balances out at this point. we see that L1 and L2, L3 are unstable points. So L3 is completely unstable, no objects can be placed, whereas L1 and L2 are marginally stable, I can say, because when you place an object, if there is no atmospheric drag or external force, then under that if there is no drifting of the satellite from the object, then those points are going to be stable. But we have to compensate the drift. If not, if there is a drift present, the slight drift even can make the object to go away from the whatever orbit we want that object to revolve around. So from that object it may move away. Okay, so that is what will happen in case of the object. Which object? That is what will happen in case of the points L1 and L2. Whereas L4 and L5 are very stable points, that is forming the equilateral triangle with respect to M1 and M2, and even if there is a drag, the third mass, test mass, will oscillate about the point but will never go out of the orbit. So this is all about the three-body problem and the Jacobi integral and liberation points. With this, I'll wind up this lecture. If there is any doubt and if you want further materials, you can mail me to professordeepthi@gmail.com. Thank you.